Anyway, how are we doing today? Doing all right? Wonderful. Why are the classrooms 5 degrees warmer than anywhere else? Like, why are the hallways cooler? I don't understand. That doesn't make sense to me. Okay. Anyway, today we're gonna have a short bit of lecture, and then we'll have our quiz. Um, so I'll talk for somewhere in the neighborhood of 20 minutes, and then we'll move on to the quiz, sort of regardless of whether or not I get through everything that we could get through for this section. Um, this section's more about kind of taking equations and connecting in the pictures and getting that sorted out. So it works better if there's self-study here, just because it's mostly acclimation with seeing examples and things like that. But we'll lay the groundwork for this, so things make sense. All right. Start off with cylinders. Okay. Um, Cylinders are include what you think cylinders are, but there are also mathematical cylinders that maybe seem a little strange. So the example that everyone's familiar with would be what's called a circular cylinder. All right. The idea being that we have this shape that I didn't do a very good job of drawing. That's probably more in line with what we expect in terms of perspective and stuff. um, what's going on here, and mathematically, the most important part of the features of this object and what makes it a cylinder, so to speak, is the fact that it features all of these parallel lines on some kind of surface. Okay, so the cylinder itself is just the exterior. Okay, when I'm speaking about shapes, I am always going to mean that the interior is empty. It's not a solid object unless I tell you that it's a solid object. Okay, so assume everything is just the boundary part, the outside, the exterior, however you want to think about it. Okay, anyway, so for the part of this cylinder shape, you can think of it as like the interior of a toilet paper roll or something, paper towel roll, whatever. It's just that edge part, right? And all of the lines that you can use to create that object are parallel. Okay. There are other types of cylinders that we could have. Such as the one given by this equation, z equals x squared, where if I draw my three-dimensional coordinate system here, we have a parabola here in the x to z plane. Okay, this equation places no restriction on the value of y. Okay, so I will also have copies of this parabola that exist in both directions along the y-axis. If I draw the picture like this, it's going to get very busy, so we're going to leave things like this. And if I were to fill in the surface, it would look something like this. The parallel lines being here, and then I'll put the ones on the interior of the surface in a different color to try to indicate what that looks like. Okay, so I have a shape, I have a surface that can be drawn by a bunch of touching parallel lines that are all mutually parallel to a particular line. Yes. Mm-hmm. So the cylinders, yes, you can think of as kind of a bent plane. Okay, you can't think of a sphere that way because sphere has different properties. It's closed. Yes. Yeah. Everything is hollow unless I tell you it's not. Is the place where we are. So when I say surface, that's what I mean. I mean just the like a thin. Imagine Imagine you have some sort of like thin, stretchable dough, like a pizza dough or something, and you're molding it into a shape. All right, but you're never going to have enough pizza dough to make the thing solid. It's a crust, not bread, I guess. That's a weird analogy. Okay. Now, when we are modeling these shapes, all right, it can be very inconvenient to try to draw three-dimensional representations, especially if we're doing things by hand. Okay, as we can see, I here can only make a reasonable approximation of these pictures. I'm not an artist. Okay, I can make something that is recognizable in simple cases for the things that we saw, and we've already seen the difference of what happens when I sketch quickly as opposed to when I slow down and take my time and do all that. Okay. One of the techniques, and this is something that's covered pretty well in the textbook, that you can use in order to indicate shapes without being necessarily a great artist or having to deal with this idea of perspective that to me doesn't make sense. The only reason that I am close to passable is that I've done this a bunch. All right. But that's just drawing simple geometric figures. I can't make something like somebody's face look right, like it belongs in space or anything like that. We're not, it's not easy to do, is what I'm saying. So these lines here, all right, these traces is what they're called, are a useful way to indicate shapes. All right. So what one might do, and what we'll see a couple of examples of here before I run out of lecture time, will be to use these traces in order to give an indication of what a three-dimensional shape looks like without needing to necessarily draw out details of that 3D shape. But let's get a couple of other examples of our surfaces before we transition to that. Okay, quadratic surfaces. All right, for us, there is a full version of the equation for quadratic surfaces that I'm not going to write down because it's not the one that we're going to be using in this section. We're going to be sticking to simple cases. All right. Missing are all of the cross terms and the terms of x, y, and z to the first power. So I can have xy, xz, yx, yz, x, y, z, all times coefficients, and those would also be quadratic surfaces. Okay, we are in this introduction just sticking to the simple case that involves x squared, y squared, z squared. Okay, but do know that those cross terms exist. Basically, what they do is they represent rotations. But We're going to leave those out to keep things simple. Okay? Yes, we can call it D if it's less confusing. It's J if you leave all of the other coefficients in, because that's just where you end up in the alphabet. All right. So if we write out this equation, all right, this is the equation of a quadratic surface. We have x squared plus y squared over 9 plus z squared over 4 equals 1. If I were to use the method of traces, what we would do is we would pick a value for one of these parameters. Z is going to probably be the easiest one to replace. All right. And if we set z equal to 0, we end up with this. Now, what is this the equation of? Yes, it's a curve, but that's not descriptive. What kind of curve? It is an ellipse. Okay. So the one that we like, I would expect everyone to recognize this, right? You need to all, in unison, very loudly now say that is a circle. Okay. All right. Okay. So that thing's a circle. This thing's close to a circle, which is what makes it an ellipse. So what would happen is we would draw a 2D axis here, x and y. All right. We have an ellipse with a semi-minor axis of 1 and a semi-major axis of 3. So we sketch this shape out here. Yes. Yeah, you are here. We chose z out of convenience, but if you chose the if you set y equal to 0, then that just means that you would need to plot in the xy plane. Okay, so this first trace is z equals 0. And if we were to choose a different value for z, what that would do is change what the right-hand side of our equation looks like. So the general practice here is instead of picking particular values, we would set equal to some, or set z equal to some arbitrary value k. And if we rearrange our equation, this is what we get. Just plugging in z equals k and then moving that to the other side. This term over here becomes negative if k's absolute value gets bigger than 2. So that puts a restriction on what values of k make sense, right? And what we'll end up with for different values of k are smaller ellipses. So if I have a bunch of ellipses set up like this, that gives me an indication that in three-dimensional space, what I'm looking at for my shape is an ellipsoid. Because if I move up or down and have different ellipses, that's what the shape looks like. Okay. It's very easy for me to draw things that look like garbage. Can't. I'm not an artist. Okay, so this is the general approach to this section. Okay. There are going to be different cases that you see. There are ellipses. All right. We'll be more specific about this. Technically, what we just drew was an ellipsoid. All right. It's an ellipsoid if it's in 3 dimensions, where the one type of cross section is, cross sections with respect to either of the planes are all ellipses. If I cut it with a horizontal plane, I'm going to get an ellipse. If I cut it with a vertical plane, I'm going to get an ellipse. That was the shape that we have here, right? That's what's going on, okay? And then our equation here tell us what the minor axes are in every direction. One of the axes is length 1, one of the axes is length 2, and the other axis is length 3. Okay. We'll do this the easy way. There's a chart in your textbook. It's easier for me to use this than it is to write all this out. Okay. So here we have 6 cases, all right? And the thing that matters the most about these cases is the basic form of the equation, okay? What you should be looking to do is count how many minus signs there are. The easiest way to do stuff is to move all of the x squared, y squared, z squared stuff to one side, and the number of minus signs you have tells you what kind of shape it is. Here, no minus signs, it's an ellipsoid. Here, if there's one minus sign and D is 0, because D here is missing, right? Then you have a cone because this squeezes down to 0. If one of your expressions here is missing, it's squared, then you have a parabolic ellipsoid. This is our first example that we talked about, or at least the first equation we gave. Okay? If there's one minus sign and this is not 0, then you get one of these 2 cases. This number's positive, then this doesn't contract down all the way. If you multiply by -1 in order to make it to where this is easier to read, this number being negative means that this pinches down early, so you end up with 2 sheets. Okay? And then this is 2 minus signs with one of your variables missing a square. Okay, so move everything that has a letter in it to one side. Okay, leave the coefficient on the other side. And then you count your squares, you count your negative signs, and then you check to see if the constant is positive, negative, or zero. Positive, negative, or zero affects what kind of hyperboloid you have. A cone is a degenerate hyperboloid that constricts to a point at the origin. Okay, and then the other hyperboloids you have are either of one sheet or two. That makes sense? Okay. If I'm giving you an exam or I expect you to have all of this stuff memorized, I will warn you. Okay. Otherwise, I expect you to look it up. But the easiest way to train yourself to get to the point to where you do remember it is you're counting minus signs and you're counting squares. Yes. I'm not looking at the right version of the textbook. The table is in section 12.6. All right. Make sense? Okay. There's one other thing that I want to do before we take our quiz. I clicked the wrong thing. Okay. There is a web-based tool here called GeoGebra that I find very useful for a lot of the stuff that we're going to be doing in this class. And occasionally I will ask you to turn in homework questions that involve use of technology. Okay. I think this is the easiest thing to use when I ask you to plot stuff. Okay. Now, if you have access to other 3D graphing utilities, MATLAB, Mathematica, whatever, I don't care if you use that. That's fine by me. This is just what I'm going to use because I can get to it without any trouble. All right. Now, you just type equations in and magic happens. Okay, this is our first example with z equals x squared. Okay, I just type the equation in, it pops up here. Our second example that we had was x squared plus y squared over 4 plus z squared over 9 equals 1. Oh wow, it's an ellipsoid. We did it. Okay. So, very powerful tool. All right. It can do simple services basically automatically if you can type in the equations. There are a bunch of other powerful things that it has available to it as well. I will do various demonstrations using this throughout the semester. I just wanted to introduce it today because it is a way for you to test things in terms of what shape it is. So one of the things that you can do is if you see an equation for one of these quadratic surfaces and you're supposed to identify what it is, you can look, see if you can figure out the answer, and then verify using technology by typing in the equation to check yourself, and then correct your intuition if it happened to have been misaligned. Okay, so that's where we're going to leave off the recording for today, and then we will transition to quiz stuff here.